Welcome back. Next, we're going to talk about monotone sequences and a powerful convergence theorem that applies to them. So let's start with some definitions. So if we have any sequence, an, we call it increasing if the terms just keep going up and up and up. Now, to be more precise, that means for every n, an is less than or equal to an plus 1. Notice here right off the bat that increasing doesn't mean that it goes up by a positive value. It could stay constant. So a sequence whose terms are always either staying constant or increasing or going up by a positive value, we will call an increasing sequence. Some people will call these sequences non-decreasing to emphasize they don't go down, but they might stay the same. But that term is confusing because it's kind of a double negative. And so we're going to call these increasing sequences if we have a less than or equal to between any two terms. That less than or equal to has to apply uniformly to all of the terms. We call a sequence decreasing if it has the opposite inequality, so it just goes down and down and down. Any term has to be the same or less than or equal to the previous term. And then we have a sort of a catch-all term that applies to any sequence which is increasing or decreasing. We call that monotone. So that means that it's always doing the same thing. It's either always increasing or always decreasing. Some sequences are monotone, some sequences are not monotone. If it goes back and forth, then it won't be monotone. So let's look at some examples. I put some sequences here. These are some interesting examples of some sequences. We're going to look at these and try to figure out, are they increasing, are they decreasing, are they monotone, are they none of the above? So we're going to start with this sequence, -1 to the n over n. I'm assuming that the domain of each of these is the natural numbers, which begins with 1. So this begins with -1. -1 to the 1 over 1 is -1. So then positive a half, minus a third, positive a quarter, minus a fifth. So notice that these terms are going back and forth and back and forth. We have a less than or equal to, and then a greater than or equal to, and a less than or equal to, and a greater than or equal to here between these terms. So this is not an increasing sequence because the terms sometimes go down. This is not a decreasing sequence because the terms sometimes go up. And therefore, this is not monotone. So this first example is a non-example. This is not a monotone sequence. The next example is n-1 squared. Here we see the terms are going up, going up, going up, going up. But the very first term, sorry, that's n-2 squared. The very first term begins with 1 and then drops down to 0. And so this one decreases, and then these increase. So for this reason, solely because the first term shows this decrease from here to here, this is not monotone. It is not an increasing sequence. It is not a decreasing sequence. It's not monotone at all. If it weren't for this event, if we erase this, that would be an increasing sequence. So that's what this sequence shows. N squared itself, 1, 4, 9, 16, 25. This is an increasing sequence. And because it's increasing, of course, then the word monotone applies to it. Often we would, to emphasize that it's monotone, we would say it's monotone increasing, but really that's redundant. What about the sequence 1 over n? 1, 1/2, 1/3, 1/4, 1/5. These are going down, right? As n gets bigger and bigger, these go down. So this is a decreasing sequence. And because it's decreasing, it's monotone. 2 to the minus n gives us the negative powers of 2. Because we're taking the natural numbers to begin at 1 as our convention here, this begins with 2 to the minus 1, which is 1/2, and then 1/4, 1/8, 1/16, 1/32. It's very different from this sequence here. But these things go down, and so this again is decreasing. Now, this last sequence, Fn, is a little bit harder to think about because the terms keep getting more complicated as we go, right? The terms here change as we go, but they don't get fundamentally more complicated. But here, the terms get more and more complicated here. So the first term is simply 1. The next term is 1 plus a half, which of course is 3/2, but I'm going to continue to write it as 1 plus a half. And then the next term is not, like, this is not the next term after that. This is the next term after that. This entire object here is the next term of the sequence, 1 plus a half plus a third, which is, of course, 1 and 5/6. But it shows the pattern better if I leave it in this form. And then the next term in the sequence is this entire number, 1 plus a half plus a third plus a quarter, which works out to be, I think, 2 and 1/12. But it's easier to reason about if we just leave it in this form. And then the next single term in this sequence would be 1 plus a half plus a third plus a quarter plus a fifth. So we would keep going in this manner. Now, the relationship between each term and the previous term is one of just adding on the next thing, right? If you have this previous term, 1 plus a half plus a third, and you're trying to figure out what the next term is, you have to add on a quarter. And if you have this term and you're trying to figure out what the next term is, you have to add on a fifth. And so every time we go from one term to the next term in this sequence, we're adding on an extra positive number. And because of that, even though the terms are very difficult to predict what their exact values are, we do conclude here that this thing must be monotone increasing, because the relationship between any term and the next term is you're just adding on some positive fraction. And so it's going to get slightly larger. And so this is a monotone increasing sequence. I want to add one more to the list just to showcase kind of a technicality. If we have the constant sequence, and it doesn't matter what the constant is, but I'll use 3. If we have the constant sequence 3, 3, 3, 3, 3, we've actually gone to the trouble of proving that this converges to 3. This is the only kind of sequence that is monotone increasing and monotone decreasing. So this is an increasing sequence, which might seem strange to say, but notice that this is less than or equal to here. This is also a decreasing sequence. And of course, twice over, it's a monotone sequence. So this is a monotone increasing sequence. It's also a monotone decreasing sequence. That's strange to say. This is the only kind of sequence that could possibly be both increasing and decreasing. So that's a bit of a technicality here, but it's important to notice that that is a less than or equal to there, and that is a greater than or equal to, and that is significant because it makes the constant sequences both monotone increasing and monotone decreasing. So this really is the right way to phrase it. You might think it would be more natural to use a strict less than and a strict greater than, but it would give us extra complexities and exceptions later that we don't want to deal with. So this is really the right definition. So these are some examples, and hopefully we showcase what monotone really means. And now, well, what's the point? Well, we've seen that any sequence that converges is bounded. And it's tempting to say that if a sequence is bounded, then it probably converges to something. But in fact, we've seen counterexamples to that. For example, the sequence 1, minus 1, 1, minus 1, 1, minus 1, 1, minus 1, that sequence is bounded, but it doesn't converge. But that sequence diverges by going back and forth and back and forth and back and forth. What if we add on the hypothesis that a sequence is not only bounded, but is forbidden from going back and forth and back and forth and back and forth? That is, what if we add on the hypothesis that it's monotone? So in other words, what if we consider a sequence which is not only bounded, but also monotone? Must that converge? And the answer is yes, and that's the content of the monotone sequence convergence theorem. We could call it the bounded monotone sequence convergence theorem, and that might be a better name, but that's just a little bit too much to say. So let's state that theorem precisely. So theorem, and this is the bounded monotone sequence convergence theorem. Let AN be a sequence which is bounded above and monotone increasing. Then AN converges. So if the sequence is monotone increasing, the only bound it actually needs is to be bounded above, and then it will necessarily converge. And if the sequence is monotone decreasing, then it needs to be bounded below. And if we think about this geometrically on the number line, it makes a lot of sense. So a sequence which is bounded above has some ultimate cap and cannot get beyond that cap. So it starts off somewhere, and then it can never go backwards. It can never go leftwards. So it must go rightwards. Maybe it can repeat a certain value several times, but then it continues going upwards. And it eventually, now I'd like to say here that it eventually reaches here and all the terms pile up here, but they don't necessarily. It could converge to an earlier value and converge to a limit here, for example, but it just can't diverge. It doesn't have any room to diverge. It has to keep moving rightward until the sequence terms pile up on some value, and that value will be the limit. It can't go off to positive infinity because it's bounded. it can't go back and forth and diverge that way because it's monotone. So the sequence terms will pile up. There is an opposite sort of situation here, which is not stated in this theorem. So let me state that clearly next. So moreover, if an is, so instead of bounded above, bounded below, and instead of monotone increasing, we'll say monotone decreasing. Then an converges. This is exactly the same principle, just exchanging left for right. So if the mirror image principle here. So graphically on the number line, what we're doing here is we're saying, look, if you have some ultimate lower bound beyond which the terms of the sequence cannot go, and then you start somewhere, I don't care where, and start moving leftward, right? Move leftward here, and the sequence terms, maybe they'll be constant for a little while, but then they'll continue moving leftward. Then eventually they're going to pile up somewhere. Maybe here, maybe to some limit prior to there, I don't know, but eventually they're going to pile up, and then when they pile up on that value, then that will be the limit of the sequence. So then it has to converge somewhere. It doesn't necessarily have to converge to that lower bound. It could converge to an earlier point, in this case a greater number, in this case a lesser number, but it will have to converge somewhere. So to sum up this situation, people will often say that a bounded monotone sequence converges. And that's a reasonable summary of this, but the phrasing here is just slightly more specific. So how are we going to prove this? This is one of the very abstract principles about sequences. We're obviously not going to crank some algebra with some absolute value signs. This is not like proving the product law for limits or the sum law for limits. We don't have anything definite to work with, right? We don't have any particular values. The sequence is almost completely abstract. So to prove this, we have to give a very abstract proof. The hardest thing here, so what we're going to do is I'm going to ignore the latter statement here, which is about a bounded below and monotone decreasing sequence, and I'm going to focus all of my attention on the bounded above and monotone increasing sequence. This case is basically the same thing upside down. To prove this, we need to show here that an converges. And the hardest thing about proving that an converges in this context is we don't know to what it's supposed to converge, right? When we take an algebraic limit and we say, okay, I've got something like the limit of n squared plus 6 over 3n squared minus 8. I'm just making stuff up here. If I take one of these algebraic limits and I want to say, oh, let's prove that this converges, then the very first step is you have to say it converges to what? It converges to maybe 1/3. And maybe you use some clever trick to figure out what it converges to, and then you have to prove that it converges to that. Well, in this theorem, we're assuming that an is a sequence. We're assuming that it's bounded above by an upper bound, but that upper bound is definitely not, is not necessarily going to be the limit. And we assume that the thing is monotone increasing. Nothing about the hypothesis here gives us a value which is going to be the limit. And there's no way to work out what the limit will be by performing algebra because we just don't have that kind of specific handle on what the sequence is. So that, to me, is the hardest part about this proof. In order to get started on proving that something converges, you have to prove that it converges to something. And there's not a something here. There's not a limit that it seems to converge to that we should prove that it converges to that. And so what are we going to do? Well, we have to figure out what it converges to. So we have to somehow make a good guess about what the thing converges to. So first of all, let's just start the proof by stating the hypotheses, which is, this is a hard enough case that we should probably make the special effort to carefully state the hypotheses. So let's begin the proof officially, proof. And so let's let an be an increasing sequence. And let's assume that an is bounded above. So what does it mean that it's bounded above? It means all of the terms of this sequence are less than some fixed upper bound. That means that there must be some value out there, some real number, which is greater than all of these numbers an. And so that does actually give us something. So then there is some bound, and it doesn't matter what letter we give it, but let's just give it cap m because it's a big number, so m for like maximum or something. So there's some bound m so that for all n, an is less than or equal to m. And it's this blue mark here, right? In this picture, the given bound is this m. Now, I would like to say, so this is just like, I'm going to make an error here. So I would like to say we'll show that the limit of an is equal to m and then continue with the proof. But as this picture illustrates, like there's no reason to suspect that the limit would be m. This is a monotone increasing sequence, and it has to converge. That's the content of the theorem. But there's no reason why it would have to converge to m. It could converge to some prior value. In fact, you could have your m, and I could have my m, which was even bigger, and my m would also be an upper bound, and it clearly can't converge to your m and mine at the same time. And so this is the wrong suspected limit. The upper bound itself is not likely to be the limit. So the next thing we have to do, instead of asserting that the limit is n, is we need to somehow get our hands on this value, the value to which the sequence converges, and then prove that it is actually the limit. So we need to somehow choose this value. How on earth can we choose it? Like, we don't even know, like, we're trying to prove that it exists. How can we get at this value? Well, the thing is, the terms of the sequence go up and don't ever go down. And so this value will be at the top of this set here. And I'm using top kind of loosely. It will be the maximum value of this set if this set even has a maximum value. But since this is an infinite sequence, this set doesn't necessarily even have to have a maximum value. In fact, quite likely it doesn't. Because if these sequence terms keep getting ever so slightly larger each time, then there won't even be a maximum value. So basically, the value we're looking for here is like a maximum of all of the values of the sequence, but it's not a maximum because it's not actually one of the terms of the sequence. So that should remind you of the idea of the supremum. So the value that we're looking for here is actually the supremum. Now let's remember what a supremum is. The supremum of a set is an upper bound for the set, but it's not just any upper bound, it's the absolute least of the upper bounds. In other words, it's the tightest upper bound. It's the minimum of all upper bounds. And the completeness axiom for the real numbers tells us that if a set is bounded above, then it has an upper bound. Now, our set is bounded above by this bound cap m. That's one of our assumptions. And so the completeness axiom of the real line applies to the set of sequence terms an and tells us that it must have a supremum. So this is really key in this proof, that the demonstration of this theorem is actually depending on one of the deeper principles of the real line. A lot of what we've done with limits so far doesn't actually hinge on this completeness axiom at all. These limits of rational functions, you can do that with or without completeness. But this theorem actually depends on the completeness axiom of the real line, which makes it just fundamentally deeper than a lot of the other concepts that we've dealt with. So what we're going to do here is we're going to identify that we have a set, namely the underlying set of values of this sequence, and it's bounded above by this cap m, and then we're going to invoke completeness, and we're going to get a supremum. So here, the set of all an, where n comes from the naturals, that's the set version of the sequence. This is bounded above by m, so by the completeness axiom, for the real line, so it has a supremum. And we'll call that S for supremum. So S equals the supremum of the set of all ANs, where N goes over the naturals. And let me remind you what the supremum of a set is, again, because it's essential to this proof. The supremum of a set is an upper bound. That is, it is greater than or equal to every element of the set. But it is not just any upper bound, it is the least among all upper bounds. And the supremum must exist for a bounded set because of the completeness axiom. Okay, so here we have the supremum. And I'm going to, very optimistically here in my diagram, I'm going to call this S. This diagram is not part of the proof. This is just how I'm managing in my brain what I'm doing. We will not be able to say, because the diagram shows the sequence converges to S, then it does, right? Like, that's baloney. This diagram is just how I'm keeping things straight in my mind. So S is quite likely not one of the sequence terms. It doesn't have to be a maximum of this set. It just has to be an upper bound. So right away, we should state what it means for S to be an upper bound at least. So because S is an upper bound, then what do we know? We know for all n, AN is less than or equal to S. It could be equal, it could be less. So that's what it means to say that S is an upper bound. It's not just any upper bound, however. It's the least among all upper bounds. Now, at this point, we should have a feeling of confidence that S is probably the limit of this sequence. And if we have that, so I mean, I don't mean that we should say we've proven it. I mean that we should suspect that that's probably the truth of the matter. We didn't even suspect that M was the limit of the sequence, but we should now suspect that S is the limit of the sequence. And if we have some measure of confidence in that, then we should go ahead with a proof and we should just claim that S is the limit, and then we should attempt to prove that. So that's what I'm going to do next. I'm going to express my optimism here. I think the limit of AN is actually going to be S, and I'm going to phrase that as a claim. And the claim will be the limit of AN is equal to S. And then the rest of the proof will be in support of this claim. Notice this claim is going to finish the job because I'm only trying to show that AN converges. If I can show that the limit is S, then I will have done that. So this claim is now the only thing left to accomplish in this proof. We need to show that the limit of AN is S. How are we going to do that? Well, again, we're going to return to the basics. We're going to go back to the definition of the limit, but because we know so little about the sequence AN, we're going to have to give a proof which is, well, we're going to have to be very careful here. So, however, we will just go back to the definition of convergence here. Notice that this is not the infinity case, right? Recent videos, we've been talking about the limit, like a sequence diverging to infinity. That is not the case that we are in. S is a finite number here. So, so this is the epsilon and definition of convergence to a finite number here. So how do we prove this? So proof of claim. So, well, we take epsilon greater than 0, right? And now there has to be some choice of n. And I really have no idea how to do that. So I'm going to leave a lot of blank space here, and I'm going to continue the proof over here. So I have no idea how to choose n, but I'm gonna let little n be larger. So let little n be any natural number, and we're gonna assume that little n exceeds cap n, and then our goal is going to be to prove that AN minus S absolute less than epsilon. So that's what we're trying to show. Now, so let's think about AN minus S absolute. Well, so why is that our goal? Because we're trying to show for every epsilon there exists a cap n. So for every little n, if little n exceeds cap n, then this is true. So we're assuming this and we're trying to take this as our goal. Now let's think about AN minus S. So AN is less than or equal to S, right? So AN less than or equal to S. And then we've got an absolute value. So what is the sign of an minus s? If an is less than or equal to s, then an minus s, just subtract s from both sides, is less than or equal to 0, which means that an minus s is a negative number. It could be 0, but it's a 0 or negative number. And that means that the absolute value here is like actually going to do something, because if the inner part is negative or 0, then the absolute value is going to flip that around. And so so notice an minus s is actually the negative of, so the absolute value of an minus s is actually the negative of an minus s, because an is less than or equal to s, which is actually equal to s minus an. So it's actually s minus an that we're trying to show less than epsilon. So here I've sort of found a way to discard the absolute value signs. So I want that less than epsilon. So, so let's do some scratch work. If I want s minus an less than epsilon, then where do I want an? I want an greater than s minus epsilon. So what I really need is an an greater than s minus epsilon. Can I have an an strictly greater than s minus epsilon? I don't know. Is that possible? Well, it depends. It depends on whether there are any ans at all in this range between s and s minus epsilon. So let me copy the picture from before, and let's have a look here. We started with an upper bound m, and then we noticed that the sequence term piled up, and we took the supremum of all the sequence terms, and that was the value s. And now let's think about where s minus epsilon resides in this picture. S minus epsilon is a little ways back. Now epsilon, you should think of it as small, but I don't want to draw it so small you can't see it. So S minus epsilon is just a little ways back from S. And what I'm really looking for here is some kind of reason why an would be greater than that. Do I have any reason why an would be greater than S minus epsilon? Sure, looks like it in the picture, but what's my reason? Well, let's remember what S is. S is the supremum of the sequence of all of those terms. What does supremum mean? It means the least of all the upper bounds. Now, S minus epsilon is less than S, and S is the very lowest upper bound you could possibly have. And that means that S minus epsilon is not an upper bound for the sequence. Now, if S minus epsilon is not an upper bound, then there must be some sequence term that exceeds it, right? So what we're doing here is we're reasoning about the definition of the supremum and the fact that if S is minimum among all the upper bounds, then this thing must not be an upper bound, and therefore it can be exceeded by one of the sequence terms. So let's write that and see where it leads us. So because S minus epsilon is less than S, which is equal to the supremum of all the ans, S minus epsilon is not an upper bound for the set of all ans, where n comes from the naturals. And so then there must be, so there is some, I'm going to say n here, there is some n for which an exceeds S minus epsilon. And for that n, let's see, I want to say S minus an. So epsilon is greater than S minus an, which is equal to absolute an minus s. So this is the right idea, but it does need a little bit of cleanup. So the idea here is, how do you get the absolute value of an minus s to be less than epsilon? You translate this to s minus an, you translate that to the fact, so that's going to be less than epsilon if and only if s minus epsilon is less than an. And then you grab an an which exceeds that value s minus epsilon because s minus epsilon fails at being an upper bound. It must fail at being an upper bound because s is the least upper bound. Okay, so to recap here, but this proof still has a problem. To recap here, s minus epsilon is less than s, which is the supremum, so it's not an upper bound. So there is some sequence term which exceeds it. And when you get that sequence term greater than s minus epsilon, then that's the same by a little bit of algebra as showing that epsilon is greater than s minus n, which is equal to this, which is the kind of equation that we want. So are we done? Well, we'd like to be done, but the notation is wrong and there's something we haven't yet done. So this doesn't actually prove the definition of a limit. So the definition of a limit says for every epsilon, there exists a cap n such that for every little n greater than that cap n, then something is true. Now, we haven't actually proven that. What we've proven is for every epsilon, there exists a little n. And then that is true for that one little n. So basically, we should be trying to show that whenever you have an epsilon, there is a cap n, and then for all little n beyond that, something is true. And what we have actually shown is that for every epsilon, there exists one little n, and then whatever, just that one little n satisfies the property. So we haven't been faithful to the definition of convergence here. How can we repair the problem? It's actually pretty simple. This one thing that allows us to say that needs to not be the choice of little n, right? Little n needs to be generically chosen, anything greater than cap n. This one thing which makes this property true needs to be the cap n. And instead of asserting this for little n, we need to assert this for cap n. Okay? Now, that still doesn't quite repair our proof, because now we're saying, well, we're basically saying the same thing in a new notation. For every epsilon, there exists one sequence term, a sub cap n, and then all of this stuff is true. So that's not quite right either. What we need is we have to get some cap n, and then we need to reason about for any n greater than that. So let's do that. So for any n greater than cap, well, actually, let's now let little n be in the naturals and assume that little n is greater than cap n. Now, do we also get this equation? Well, s minus a, well, the absolute value of a little n minus s, which is the actual term of interest, is still equal to s minus that value. Now, here, I'm going to put in a critical inequality here, which is that is less than or equal to s minus a sub cap n. So this inequality is really key to getting everything to work. And then I'm going to put in less than epsilon. But let me justify this. This is all hinging on the fact that the sequence is increasing. And if you pay careful attention here, I haven't actually used that hypothesis yet. It is getting used here once and only once in this whole setup. Here, I'm comparing s minus a little n to s minus a cap n. And the relationship between a little n and a cap n is caused by the fact that the sequence is increasing. A little n is greater than or equal to a cap n because little n is farther down in the sequence. So a little n is the larger. Here we are subtracting the larger. Here we are subtracting the smaller. And so this one is less than this. And so this inequality here is caused by the fact that so a cap n is the lesser and a little n is the greater value in this sequence because little n is farther down. And so that gives us this inequality, which gives us a minus s is less than epsilon. And now you see I've kind of betrayed myself by being so formal to stick to the template of this proof. Now I've got things all backwards. I've got a choice of cap n going on right here, and then some algebra, and I'm figuring out what that is. And then I've got an assumption about little n happening here, but again, happening here. So this is an easy repair. All I have to do is erase this. Because, oh, and this. Because the choice of cap n actually occurred here. This shows the existence of some cap n, and this is the correct situation where we should introduce the little n and assume that it's greater than cap n. So I just want to emphasize here that this proof really does now have the right structure. It takes an arbitrary epsilon, it gives some reasoning, proves that there is a cap n, takes a little n to be arbitrary, assumes it greater than that, and then proves that an minus s is less than epsilon. So the broad skeleton of this proof, as it is now written and rewritten, is that it establishes that this sequence converges to S. So we've proven now that the sequence an converges to its own supremum, and that's enough to say that it is a convergent sequence. So we have any increasing sequence with an upper bound must converge. For the other case, you can say, let's just do the same thing with the infimum instead of using the supremum. Or you can say, let's just take the negative of the sequence, which will flip left and right and apply it to that. There are various ways to take care of the other thing. The easiest way to take care of the other direction is to say, it's similar enough that I'm not going to do it, and that's going to be my approach.